So one important thing I will use is whenever I have an ordinary category and a class of arrows in it that I would like to invert, there is an infinity category where these arrows have been inverted. Well, first of all, so if I invert no arrow, so if C is an ordinary category, I can view it as an infinity category. Denoted nerve of C. So I use this notation because in the model of quasi-categories, this is literally the simplicial set given by the nerve of C. And more generally, if I have a collection of weak equivalences in C, so if there is a collection of morphisms in C, so a collection W of morphisms in C, one can construct the infinity categorical localization. And the notation I'm going to use is just nerve index WC. So this is the infinity categorical localization. So I told you one model for infinity categories is simplicial categories. So if that's your preferred model, then there is a very classical description of this infinity category, which is given by the Dwyer-Kahn hammock localization. But if you use other models, there are other constructions for this. So essentially, that's how you embed classical homotopy theory into infinity categories. Classical homotopy theory, you're in a situation where you have a category and a class of morphisms that you would like to invert. And this is how, and there is an infinity category that encodes this situation. So an infinity category has a homotopy category. Which I'm going to denote O of C, where C is some infinity category. And as you might expect, the homotopy category of the localization of some one category at a class of morphisms will be just one categorical localization. So something that's usually called a joint W inverse. And maybe one thing I can say, so we know we're usually familiar with one particular examples of such a category with weak equivalences, namely the theory of model categories, like homotopy limits, homotopical limits, etc. This still works. You can do this in infinity categories, but everything that is sort of model dependent, you can't. It doesn't really make sense. So the infinity category is really just you remember just the minimal amount of data so that you can do homotopy theory and nothing more. All right. Yeah, one thing also that I'd like to say is you can talk about symmetric monoidal infinity categories. And well, that's not so difficult. So essentially, it's based on the a much older idea of Siegel that you can encode infinite loop space by what's called gamma spaces. That's the way you can encode a homotopy commutative multiplication in homotopy theory. And here what you do is, a symmetric monoidal category is a functor from the category of finite pointed sets into infinity categories, which satisfy the Siegel condition. So I won't explain the Siegel condition in details. If you know about Siegel's work on infinite loop space, you'll know what I'm talking about. And usually you don't quite, you use what's called the straightening and straightening principle, which tells you that you can encode such functor equivalently. You can encode it as fibrations over this category thin star. So equivalently, I never remember if it's cool. So co-Cartesian, I think it's co-Cartesian if you look at covariant functors over thin star satisfying some Siegel condition. So yeah, it's not that bad actually. A symmetric monoidal infinity category, just some diagram in infinity categories. And maybe just one fact that we'll use. So if we're in this situation here, where we have a category with a collection of weak equivalences, so if C is in one category with a collection of weak equivalences, W, then the infinity categorical localization will inherit an infinity category structure if a certain condition is satisfied, and the condition is quite natural. So assume that for all x in C and all morphism in W, the induced map x tensor A to x tensor B is a weak equivalence. Then the infinity categorical localization inherits symmetric monoidal structures. So in particular, one example of this situation is if you have a model category with a tensor symmetric monoidal model category, then the axiom for symmetric monoidal model category tells you that this is true if you restrict to cofibrant object. Tensoring with a cofibrant object will preserve weak equivalences. So it tells you that if you have a symmetric monoidal infinity category, you can restrict to cofibrant objects, and that the tensor product will restrict to this category. And then you can do infinity categorical localization, and you get a symmetric monoidal infinity category. Okay, so that's all I'm going to say about infinity categories today. And I'm just going to use them at a very specific place in my talk. So, okay. Okay. So now I'm going to talk about something completely different, and then I'm going to explain how you can put these two ingredients together. Namely, now I'm going to talk about mixed Hodge structures. So this is much more classical mathematics. So let me start with the definition. So a Hodge structure. So I'm going to start by defining a pure Hodge structure. Say over Q. Of weight n is a Q vector space, is a finite dimensional Q vector space. V together with a decomposition of V, the complexification of V. So when you extend the scalars from Q to C, you get a decomposition as a direct sum of terms. And you don't just get any decomposition. With the property that UPQ bar is equal to UQP. So what do I mean by UPQ bar? Well, when I tensor with C, I have a complex conjugation acting on this C factor here. So this gives me a linear, of course not a C linear, but certainly a Q linear endomorphism of this vector space. In fact, it's R linear. And UPQ bar is just the image by this endomorphism of UPQ. Yes?
So the decomposition is Q vector space.
Well, you can actually check that it's even a decomposition as C vector spaces. Yeah, even so. Yeah, I said that this complex conjugation endomorphism. Of course, it's not C linear, but it's like C and T linear. So it sends a C vector space to a C vector space. So this is what a pure Hodge structure is. And now what is a mixed Hodge structure? Yeah, maybe before defining a mixed Hodge structure, I have to say one last thing. So we can alternatively encode pure Hodge structures using one can introduce the so-called Hodge filtration. Defined by Fp of V, maybe Fm of V is direct sum for P greater than of V tensor C is direct sum for P greater than or equal to M of these UPQ. So this is a decreasing filtration on V tensor C. And the data of this decreasing filtration is exactly the same data as this decomposition. Because, well, this decomposition is just the associated graded for this filtration. So now I can define what a mixed Hodge structure is. So it looks quite complicated at first sight. So a mixed Hodge structure is the first piece of data is a finite dimensional Q vector space. V. The second piece of data is a increasing filtration on V called the weight filtration. W on V. So it's called, W is called the weight filtration. And the third piece of data is a decreasing filtration F on V tensor C. Such that on the associated graded, on the nth term of the associated graded for W filtration on V, I require that this the induced filtration F is a pure Hodge structure of weight n. So on GR n W V. So this is the nth stage of the weight of the associated gradient for the weight filtration. The filtration F. So maybe like this. The filtration F induces a pure Hodge structure of weight n. So essentially, it's something that is built out of pure Hodge structures by certain types of extensions. That's how you build mixed Hodge structures in general. Okay, so they form, these objects, they form an abelian category. So yeah, this is not completely obvious because, like, if you just take, for instance, filtered vector spaces, this is not an abelian category, but this one is. And it has a tensor product, which is what you expect. You just tensor, you know how to tensor filtered vector spaces, and you can check that this this condition will pass to the tensor product. So this is an abelian tensor category, a tensor category. It's also what's called rigid. So any object is dualizable in this symmetric monoidal category. And the dual is just, well, takes the linear dual and takes the induced filtrations, the linear dual. Okay, well, why do we introduce this very complicated looking category? We have a theorem which is due to the ligne. And it says that the cohomology of algebraic varieties over the complex numbers is naturally equipped with a mixed Hodge structure. So let me state it like this. If there is a natural mixed Hodge structure on the cohomology of X with Q coefficients for X a complex algebraic variety so what I mean by natural is, yeah, maps of algebraic varieties will induce maps of mixed Hodge structures. And this structure is also compatible with the cup product. So of course, the rational cohomology of algebraic varieties as any space has a cup product, and the cup product will be a morphism of mixed Hodge structure. So it works in general, but it's true that in my talk I'm just going to talk about smooth varieties, but it works in general.
Are the increasing and decreasing fluctuation in unique correspondence?
Well, no more than what I've written. So yeah, I think the definition I've written is correct. So yeah. So well, how can you prove this? Yeah, let me look at my notes. Yeah, and maybe let me say one more thing. This, in the particular case, so if X is smooth and proper, so proper you should think of as the algebrogeometric analog of compact. Then, if you look at the ith cohomology group of X, so because of what I've said above, it's a mixed Hodge structure, but in fact, in that case, it's a pure Hodge structure of weight I. And in general, how you can sort of construct the mixed Hodge structures on non-proper algebraic varieties by sort of inducing it from the case of proper algebraic varieties. So the way it works is so here's a very brief idea of where this comes from. So I'm going to admit that in the smooth and proper case, it works as I said. And essentially, well, this decomposition comes from the decomposition of differential forms in terms of well, you know, if you take a complex variety, the differential form they decompose in such a way. Like the real differential forms. Well, I mean you take the complexified real differential forms, and they will split in such a way, and this is what will induce the Hodge structure on the cohomology. But then to go from the smooth and proper case to the general case, you use the so-called weight spectral sequence. So yeah, the way it works is if X. So let me just explain the smooth case. So if X is smooth, there is a theorem of Nagata that tells you that you can embed it into a X bar called the compactification. and x bar minus x is what's called a normal crossing divisor. So divisor you should think of as a codimension one. Codimension one sub variety. And normal crossing is like locally it looks like the standard hyperplanes in CN. Like coordinate hyperplanes in CN. And so what you can do is do the Le Resser spectral sequence for the inclusion of X into X bar. So, it gives you a spectral sequence which will converge to the cohomology of X. On the E1 page, you can compute it as, let me check. HT minus 2S. Well, it's not so important. DS with Q coefficients. So DS is just the disjoint union of all S-fold intersection of components of my divisor. So my divisor is a bunch of smooth components that intersect. And well, DS is like the intersections of codimension S essentially. So my spectral sequence looks like this. And because of course, these are cohomologies of smooth and proper varieties. And so what I get is, because for any spectral sequence, I actually, you get a filtration on the target, whose associated gradient is the infinity page of your spectral sequence. In that case, actually, the spectral sequence collapses at E2, but in any case, you get a filtration here, which will be the weight filtration. And you see that the associated gradient, there will be cohomology groups or like sub-quotient of cohomology groups of smooth and proper varieties, so they will be pure Hodge structures. And that's how you get the Deligne theorem. What's non-trivial? It looks very non-functorial here because compactifications are not natural. But it turns out that from the E2 page, well, the E2 page is also the last page, but the E2 page is actually natural in X, even though the E1 page is very dependent on this choice of compactification. So all of this is proved by Deligne. It's by no means easy, but that's sort of how it goes. You mean varieties defined over a field of positive characteristic, or? But you want for the coefficients of your cohomology to be of positive characteristic, or the field of definitions of your varieties, the coefficients. So for the weight filtration actually exists for any fields of coefficients. So what you see, this spectral sequence, it really doesn't depend on having Q here. It would work for any field of coefficients. So the rate filtration actually exists. But of course, well, the fact that there is this mixed Hodge structure is very specific to being with coefficients in Q. If you're with coefficients in some other, like in a positive characteristic field, for instance, you'll have things like maybe Galois actions on the cohomology. So the weight filtration is a very general thing, and then there will be additional ingredients that tells you in some cases this weight filtration splits. And this is this kind of idea that we're going to use. Why does a spectral sequence degenerate? Yeah, well, you have to read Deline's paper, I think. Well, yeah. Yeah, I don't know. Sorry. Yeah, and maybe yeah, one last thing I'm going to say. Yeah, this. So this is the end of my proof. One last comment is that this mixed Hodge structure on the cohomology of varieties is also compatible with the Kunes isomorphism. So if you have two varieties X and Y, well, the cohomology X cross Y is the tensor product of the cohomology of X and the cohomology of Y, and this is an isomorphism of mixed Hodge structures. Yes. Okay, so now I'm going to state a theorem which is due to Deline also, which is called the Deline splitting theorem. And it says that if I have a mixed Hodge structure, there is a natural way to split the weight filtration. Naturally splits over C. And moreover, well, I'm saying a little bit more, it splits as in a symmetric monoidal way. So over C in a symmetric monoidal way. So let me state a more precise result. So there is a factorization so to the mixed Hodge structure, I can go to vector spaces over C just by sending V to the V tensor C. And the claim is that this functor lifts to graded vector spaces. Well, this functor is just the totalization, like just take the direct sum. If you have a great vector space, you can take the direct sum of all the pieces and get a vector space. Yeah, this functor is the associate gradient for the weight filtration tensor with C. So of course, well, for whenever you have a filtration of a vector space, it splits. You can always pick a splitting of any filtration, but it's usually there are many choices. And Delin actually, the way he proved this is very explicit. He writes down a formula of a splitting that is completely functorial in the mixed Hodge structure. So he uses the data of the other filtration, the Hodge filtration, to produce such a splitting. Yeah, and what I mean by symmetric, all these functors are symmetric, are like symmetric monoidal. Well, in fact, they're even symmetric monoidal. And actually, so this theorem you prove very explicitly, and then you can deduce from it in a much more abstract manner. And that's something we wrote in our paper with Joanna. So I don't know, well, I'm going to put her names because it's the only place I know where this is proved, but I expect other people would have noticed this. From this splitting over the complex numbers, you can actually deduce a splitting of the weight filtration over Q, actually. So the same result works. Over Q, meaning that you can produce a diagram, a similar diagram, but now you don't tensor with C anymore. So this is just the associate gradient for the weight filtration. This is forgetful, and this is also a totalization functor. And again, all these functors are like symmetric monoidal. And the kind of techniques we use to prove this are very similar actually to what Damien was talking about, like this theory of associators. So for associators, you can write down explicit associators over C or over R using differential equations. And then sort of by abstract nonsense, once you have an explicit associator over R, like you know that the set of associators over R over C is non-empty, you can deduce that the set of associators over Q is non-empty. But it doesn't give you a way to write one down. So it tells you that the set is non-empty for abstract reasons. That's exactly the same kind of method that we use. So one caveat is, certainly, it's not true that the natural splitting that we get, if we tensor it with C, we recover Dolin splitting. It's like it's much more subtle than this. It's like we just show there is no obstruction for the existence of splittings over Q. But we can't really put our hands on one such splitting. Okay, so now I can state the theorem that we proved, Joanna. Well, I'll have to introduce one last piece of definition. So I'm going to call smooth algebraic variety over C. Is called alpha pure. So alpha will be some non-zero rational number. The smooth algebraic variety X over C is called alpha pure if I take the kth homology group of X with coefficient in Q, this is is a pure Hodge structure weight alpha k whenever alpha k is an integer and is 0 otherwise. Alpha times k. Alpha is a rational number. K is an integer. 0 otherwise. So for instance, if you say a variety is 1/2 pure, it would mean in particular that its cohomology would be concentrated in even degrees because you have this condition here. So, well, an example, yes, there is a question. Yes.
I thought pure it was with respect to the integer. No?
I think it's, well, yeah, you can certainly, there will be examples where alpha is an integer, but this is a bit more general. So examples, well, we've already seen one example. So smooth and proper. So this is the theorem of Deligne that I've stated at the beginning. So for smooth and proper variety, I told you that the kth cohomology group with a Hodge structure of weight k. So they're 1 pure. Okay. But let me give you examples that are not 1 pure. So here's another example. Take C minus 0. C minus the origin is too pure. And actually, it's quite a fun exercise to compute this. I mean, well, in this particular case, it's very easy. What we do is we consider the inclusion of C minus the origin. Well, you can of course embed this into C, and you can embed this into P1. So yeah, you know that you can construct P1C by gluing together two copies of C minus 0. Two copies of C along their intersection, which will be C minus the origin. So you get a Mayer-Vietoris long exact sequence. And all this theory of, well, I haven't told you everything about these mixed structures, but the theory is sufficiently nice, like the construction is sufficiently nice that this will be compatible with, for instance, if you have a covering of your variety by two open sets that are themselves varieties, the long exact Mayaviettori sequence will be, all the morphisms will be morphisms of mixed Hodge structures. So in that case, you know that the second cohomology group of P1, if you write the long exact sequence for the covering of P1 by 2 copies of C, you will see that the second cohomology group of P1 is identified with the first cohomology group of C minus the origin. And this identification will be as mixed Hodge structures. And this, because P1 is proper, this is pure of weight 2. So this is pure of weight 2. And the H0, well, the H0 will always be pure of weight 0. So this is 2 pure. You have 2 cohomology group, H0, which is pure of weight 0, and H1, which is pure of weight 2. But let me give you an example where alpha is not an integer anymore. So now, let me look at x is C to the D minus the origin. So this is homotopy equivalent to a 2D minus 1 sphere. So there is one cohomology group in degree 0, one cohomology group in degree 2D minus 1. And the cohomology group in degree 0 is of weight 0. And let's try to compute the weight on the cohomology group in degree 2D minus 1. And for this, we can use a slightly different ingredient. We can use the fibration. If I take a quotient of C to the D minus 0 with respect to C minus 0, the quotient is really P D minus 1. And you can compute the cohomology of the middle term using a Serre spectral sequence. So a Serre spectral sequence. And again, you can show that the Serre spectral sequence will be compatible with the mixed Hodge structures. So it tells you that, well, you have a spectral sequence with E2 page is H. It will be the cohomology of the base. Answer the cohomology of the fiber. And it converges to the cohomology of the total space. And now, well, we know the cohomology of all of the terms. So in the spectral sequence, it will look something like this. So we have the cohomology of P D minus 1. So we have one cohomology group in each even degree from 0 to 2D minus 2. And then we have another copy of this, which corresponds to the H1 here above, like this. And we know what happened in the spectral sequence. The only class that survive are this one, and all the others that sort of kill each other. And of course, well, just by counting weights, you see that this class will be represented by something which comes from H1 here and H2D minus 2 here. So this would be weight 2D minus 2, this would be weight 2. So when you sum, you see that H2D minus 1 of CD minus 0 is of weight 2D. So the conclusion of this is that CD minus 0 is 2D divided by 2D minus 1 pure. So this gives you an example where alpha is not an integer.
In space, it's easy to see that it's just one generator.
Yeah. Yes. Yes, I agree. In fact, so using similar ideas, you can prove so let me give another example, and I'm not going to give the details. So more generally, so if VI is what we call a good, I'm going to define this in a second, a good arrangement of codimension D subspaces of C to the N. Then the complement is the same level of purity, is pure, is, sorry, 2D divided by 2D minus 1 pure. So this would be a very trivial example where you have just one subspace, which is 0, which indeed has codimension D. But you have this level of generality and good arrangement. So it's something a bit similar to general position, but a bit more general. So we call it a set of codimension D subspace is called a good, so of Cn is called a good arrangement. So it will be sort of an inductive definition. So if there is just, say, 0 or 1 subspace, this is fine. But then if you have more subspaces, you require that, so, well, if, let's say if one of the following two conditions holds, so if either 1 or 2, so condition 2 is for each V in the arrangement, the set of intersections of V with the other subspaces is a good arrangement dimension D subspaces of V. Maybe I should have said this is only defined if my set is finite. But you see, so when I consider this, I have one less subspace here because I look at intersection of the other subspaces with V. So inductively, this gives a good definition. So I think, so hyperplane arrangements always satisfy this. But in bigger codimension, you can construct arrangements that are not good. Yeah, and yeah, I've told you. Yeah, the punchline is that the complement of such arrangement are pure in that sense. But an example of such an arrangement, which is, I think, one of the running examples in this conference, you consider the space of configurations of points in Cn of ordered configurations points in Cn. So yeah, this space conf and Cn, sorry, maybe let me call it D. So this is C D to the n minus all the diagonals. So delta ij is the inside CD to the n. You look at the subspace where point I and point j coincide. And by definition, the space of configuration is the complement of all these diagonals. So you require that any 2 points are different. And this, yeah, this is a good arrangement of codimension D subspaces. Well, this is a complement. Switchboard, please. Bruno. Someone is asking for you to switch boards. But maybe it was. I received this as a private message, so but hopefully now it's good. Okay. What time is it? 10. Yeah. Okay. So now let me state the result we prove. Now that we have a few examples. Theorem we prove with Johanna is the following: the singular chain functor with Q coefficients, say on smooth varieties. So from smooth varieties over C, which are alpha pure. So hopefully the notation is self-explanatory. So the full subcategory of the category of smooth varieties over C, whose cohomology is alpha pure. 2 chain complexes over Q is formal as a lax monoidal functor. Morphisms of algebraic varieties. Yeah, so one observation is, of course, schemes that are like smooth varieties that are with alpha pure cohomology are stable under Cartesian product by the Q-net isomorphism. So the statement I had about the Q-net isomorphism being compatible with mixed Hart structure, you can deduce from it that this category is stable under Cartesian product. So this really forms a symmetric monoidal category. and the statement is this. And there is sort of a dual contravariant version of the theorem that we also prove. So it's like a cohomological version, and in order to really have the problem is if you take singular quotient, this will not be a lax monadal functor anymore. So we use instead Sullivan's differential forms. So Sullivan differential form functor, so omega star PL from the opposite of this category to chain complexes over Q is formal. As a lax blah blah blah, as a lax monadal functor. Yes, it's also, well, I think it follows from this because any object in the source is a commutative algebra. So since it's formal as a lax monadal functor, it sends commutative algebras to commutative algebras. So it's a consequence of what's on the board. You can, if you want, you can replace the target by CDGAs, and this will still be true. Yeah.
Does one imply the other, or I mean, are you put them completely independently?
I mean, the proof is completely parallel, but I think there is no implication going one way or the other.
No way to compare them in some sense.
I mean, at the, yeah, I think, so the point is at the infinity categorical level, you could state just one theorem, which is that, well, either of these is formal as a strong infinity monadal functor, but the problem is neither of these is actually a strong monadal functor at the one categorical level. So that's why I stated them as two different theorems. So yeah, what you see is, so in fact, infinity categories enter in the proof, but the final result is completely old school language, like the language I introduced yesterday. So let me now give a quick sketch of proof. It's really not hard with everything I've introduced. So let me give you an almost proof. Yeah, maybe before going into the proof, maybe one comment that I want to emphasize is that I commit to an alpha. So I fix alpha once and for all. And you have one result like this for each choice of alpha. I'm not saying, yeah, I'm not considering alpha pure schemes where I allow myself to vary alpha. Alpha is fixed once and for all. And the proof, well, I'm going to give a proof in the case where alpha equals 1. But the idea of proof works the same for a general alpha. It's just to be able to use what the proposition I had yesterday. And the way it works is, well, you have this category of smooth one pure algebraic varieties. And we know that the cohomology has a mixed Hodge structure. And maybe let's pretend that you can lift this at the level of chains. So let's say that there is a functor to chains in the abelian category, chain complexes in the abelian category of mixed Hodge structures, which is as good as you'd like. So it's symmetric monoidal. And when I forget the mixed Hodge structure, it recovers singular chains. So let's pretend that there is such one such functor. Then I can use Deligne splitting. But let's say the version that we proved over Q. And it tells me that this can split the weight filtration. So, sorry. Graded, I land in chain complexes in graded vector spaces. And the effect on homology, by assumption, I apply this to things that are one pure. So in homology, the nth homology group is supposed to be pure of weight n. So this is what I called yesterday. Well, yesterday I just called them pure, but now let me call them one pure. So these are graded vector spaces, such that on homology, chain complexes in graded vector spaces, such that in homology, the nth homology group is concentrated in weight n. And then I have the forgetful functor to chain complexes over Q. So this is over Q. And we saw yesterday that this is formal. So that's from yesterday's lecture. And of course, pre-composing a formal functor with any lax monoidal functor still gives you a formal functor, because you can just pre-compose your zigzag by whatever this part is. So this implies, the claim is that this composite is quasi-isomorphic to the singular chain functor. So this implies that the singular chain functor is formal. So essentially, you see that this works modulo being able to put the mixed Hodge structure at the chain level, such that, being able to promote the singular chain functor to a functor which lands in chain complexes of mixed Hodge structures. Okay, so this is our almost proof, and the way we make it work, instead of, well, I don't know how to make a functor like this directly, but if you look at the literature on mixed Hodge theory, people introduce what they call a mixed Hodge complex. So, you can associate to any smooth variety what's called a mixed Hodge complex. And I'm not going to define what a mixed Hodge complex is, but maybe it's a more relaxed version of a chain complex in mixed Hodge structures. So it's like it's a chain complex over Q that has two filtrations. But I don't really require that at the chain level they form a mixed Hodge structure, but when I require that when I go to homology, they form a mixed Hodge structure. So essentially, almost formally, there is a functor from chain complexes in mixed Hodge structures that go to mixed Hodge complex. What we do is, so this functor is certainly not an equivalence of categories, but it's, this functor this induces a symmetric monoidal equivalence of infinity categories from using my notation from before, the localization at the quasi-iso of chain complexes in mixed Hodge structures to the localization at quasi-iso of mixed Hodge complex. And maybe, yeah, I should say this. This result, so it's not said in this language, like in the language of infinity categories, but it's actually due to Bailinson. So what Bailinson in fact proves is that this functor induces an equivalence at the level of homotopy categories. But it turns out that in that case, since both the source and the target are what's called stable infinity categories, being an equivalence at the level of homotopy category implies being an equivalence of infinity categories. So Bailinson really proves what I wrote on the board, even though he doesn't say it. And this is, yeah, so now now you have this sort of zigzag of functors from smooth schemes to chain complexes and mixed sort structures. And you can replace the zigzag by just one functor but the price you have to pay is to move to the world of infinity categories. So now, well, the observation is that this implies that the almost proof above works if you move to the world of infinity category. Well, the problem is, so you get an infinity categorical formality result. So what you get is a single chain functor is formal as a lax middle infinity functor, which is a priori a bit weaker than what I defined before. So it means that it's connected to its homology by an equivalence in the infinity category of lax monoidal functors from smooth. So it's formal as an infinity functor, but then we can apply a rigidification result due to Hinich. So Hinich showed that you can form a model category of lax monoidal functors in the lax monoidal functors in the ordinary sense. And you can form the infinity category of lax monoidal functor in the infinity categorical sense. And these two, if I take the underlying infinity category of the model category, it is equivalent to the purely infinity categorical definition. So in fact, this implies that the singular chain functor is formal in the old sense. This result of Hinich is certainly not trivial. But on the other hand, if you're a believer in infinity categories, you should not even care about this, and this should be good enough for any purpose. Okay, so I have 10, 15 minutes left. Yeah, maybe let me give a few examples of applications of this. So I have we have a covariant and a contravariant result. And both of them have applications. Of course, well, the GNPR paper is it fits in this theorem, and it's actually the case alpha equals 1. So we said that for smooth and proper varieties, the cohomology is 1 pure. So the overlap is not perfect because for them it's compact Kähler manifolds. Here it's smooth and proper. Well, I mean it's smooth schemes with 1 pure cohomology, which includes smooth and proper varieties. So neither of this set of objects is contained in the other. But all the examples I know live in the intersection, actually. So yeah, for instance, the example they give of this operator of compactified moduli spaces, it's certainly also like you can use our theorem to prove it. And what you see, well, one thing I like about this theorem is that, yeah, contrary to GNPR theorem, our theorem is over Q. And so if we've hidden this descent of formality problem in actually the descent of the Deligne splitting from R to Q. So yeah, example of applications so maybe I'm going to call this one A and this one B. So we can, yeah, maybe, well, I actually started thinking about this kind of questions when Bruno asked me if a certain opera introduced in one of his papers with Dotsenko and Chadrin is formal. So it's like there is this non-commutative framed little disks opera. So that's an opera that was introduced by Dotsenko, Chadrin, and Ballet. So it's a non-symmetric opera, and it's so the non-commutative little disk opera is it's just in arity n, it's a product of n minus 1 copies of the circle, and the opera structure is a bit silly. It's just you just insert copies of the circles. Well, yeah, let me. I don't think I want to give too much details about this, but the point is, yeah, you can show this. Yeah, this is an opera. You can find a model. There is a model for this that lives in smooth schemes that are too pure. So it's just going to be a product of copies of GM, C minus the origin. And therefore it is formal. Of course, I think now, well, Bruno told me, I think a while ago, that you can have a very direct proof of formality that doesn't use this kind of technology. Yeah. But let me give, yeah, another example that I like a lot. So there is something which I called Casanav's monoid. So this was something introduced in Christophe Casanav's PhD thesis. So it's a monoid structure. You take the disjoint over all integers, non-negative integers of what's called Fn. Fn is the variety of degree n pointed maps from P1 to P1. So degree, yeah, what I mean by degree n pointed map is just a degree n rational function. Say, well, to fix ideas, you can say pointed. You can, for instance, say that they send infinity to infinity. So essentially, it's the data of two polynomials that are co-prime, where the top polynomial is degree n, and the bottom polynomial is degree at most n plus 1, so that it really goes to infinity at infinity. So it's really it's a smooth schemes. It's a complement. Such a map is defined by you just have two polynomials, so you just have to determine to say what the coefficients are. So it's a complement of some subvariety in some big C to the n. And one cool thing that Cazenave did is that he shows that at the algebra geometric level there is a monoid structure in this collection of objects that sort of mimics the compositions of maps from S2 to S2. So there is a monoid structure on this space, which is algebraic. So it's really induced by maps of schemes. And is sort of homotopic, or I don't know how to say it, compatible in a homotopical sense. With the loop space structure on pointed maps from S2 to S2. So this is just like continuous maps from S2 to S2 that send infinity to infinity. This is a two-fold loop space, or in particular a one-fold loop space. So there is a monoid, at least up to homotopy structure. And this is algebraic maps from P1 to P1. And of course, any algebraic map is a continuous map. So there is a map from this to this. And yeah, what Cazenave has a monoid structure here, which yeah, is compatible with this one. And so what you can deduce from our theorem is that we have that chains over this disjunct union with Q coefficient is formal as a DGA. And maybe, yeah, one last example, which is a bit more, is based on more recent work. So we come back to the little disk operad. So using work of Weintraub. So I think Damien mentioned this yesterday. So what Weintraub does is he produces an algebraic model for the little disk operad. It doesn't quite live in smooth schemes. Actually, it lives in something a bit more general. It lives in log schemes. So Weintraub, he constructs so I'm not going to say anything about log geometry. Whose complex points recover the, so he gives a version for the framed and the non-framed little disks operad. In fact, yeah, our log schemes are still close enough to schemes to have a perfectly well-defined Hodge structures and under cohomology. And in fact, you can lift it at the level of chains in a similar way to what we did in our proof. So in fact, you can deduce from this, and Weintraub has a paper about this actually, you can deduce that you can recover formality of these two operands. And let me just say a word about theorem B. Yes. Applications of theorem B. Well, of course, so theorem B tells you that, for instance, a complement good dimension D arrangements are formal over Q, meaning in Sullivan's sense, so as CDG is, omega star PL is quasi-isomorphic to cohomology. Well, I think, well, probably that was known before, at least for hyperplane arrangement, certainly. Yeah, another example is what's called complements of toric arrangements. And that's due to Clément Dupont, actually. But again, I think, yeah, his paper is only over R, whereas R is over Q. Yeah, and in general, yeah, maybe what is a toric arrangement? You just take a product of copies of GM of C minus the origin, and you look at the a toric arrangement is the kernel of a group homomorphism of the form Z1 to the A1 times Z2 to the A2 times Z3 to the A3, something like this. And the complement of the kernel of this is what's called the complement of a toric arrangement. And you can show that these varieties are actually they're actually two pure. Yeah, but so one thing also that follows from our result, which I don't know, maybe there are Paulo or other rational homotopy theorists who are in the audience can tell me. I think our result, this formality over Q, I'm not sure it was known in full generality without nilpotence assumptions on the space, because you have Deligne-Griffiths, Morgan Sullivan give you formality over R, and then you can use results of descent of formality to get formality over Q. But these results usually rely on some kind of minimal model machinery that requires nilpotence assumptions. For us, it's like direct. You don't have any nilpotence assumptions, and this maybe was not known before. I'm not sure. Yeah, and so therefore, yeah, our machines have shortcuts it. So I think, yeah, the fact that you have formality over Q instead of over R is quite interesting. And maybe it's a good time to stop.
Yeah, that's what I would say.
Whereas from background, so you actually establish a formality.
Yes.
Is there any possibility of perhaps falsification? I imagine that's difficult.
No, I think there is. I mean, the existence of a associated over Q is essentially equivalent. What?
So it's not that rational system.
Mm-hmm.
No rational associated.
Yes. But here it's sort of similar, where like the existence of associated is very similar to the existence of the linear splitting over Q. So it's sort of, yeah. I mean, yeah, existence of associated is sort of related to the theory of periods, which is something like Betti-Durham isomorphism in cohomology, and this is also related to the Stalin splitting results. So all of these things are sort of tied together. There's some kind of very non-trivial choice of isomorphism between two complicated objects. So there is sort of a natural choice over C, and then there is you can descend it by abstract nonsense to Q. But yeah, I guess these three results is like yeah, there is something explicit you can do over C and then deduce it over Q, but no direct comparison.
So I'm curious about this. So you say that you have a model that is the space for non-present. I don't understand.
So it's what's called a non-commutative Fresnel
Yeah,
discrete.
so what does it mean? I mean, you have a space and you have no How can a space model and no?
What do you write? There is a model.
There is a model for this that lives in.
Right. So what I'm saying is there is an operad in this category,
And no present. Okay.
which when you topologically realize gives you the. Yes, Paulo?
It just came to my mind, you know that as an anomaly that actually such things, topological phases that
Yes. Is the other one? Yes. Yeah.
now it came to my mind. How about if the blank of opera takes like
Yeah, that's a very good question. That would be really cool.
I think I have a question on the chat. Does the Philippine counter capture more information than the simulation?
I would say no. I mean, it depends what data you attach to a simulation functor. If you view it a functor to E infinity algebras, I think they capture the same information.
Can I ask a question? So I was wondering whether you could comment on connections to like higher structures here. So like mixed Hodge structures on. So I know Joanna has done some work in this direction on putting mixed Hodge structures on like minimal models. You could equivalently formulate that as having these structures on the like the C infinity minimal C infinity model or L infinity model. I was just wondering whether you could make some comments in that direction. I mean, maybe this is more a question for Joanna, but how do the mixed Hodge structures on the cohomology interact with the minimal C infinity structure, etc. in the cases when this is non-trivial?
Yeah, I don't know. Maybe Joanna is in the audience, or okay. So maybe she can answer this question.
I'm here, but full of kids around me. So actually, all these things that Geoffroy explained, I think, are functorial generalization of these minimal models and the mixed Hodge structures. Actually, the equivalence of symmetric monoidal categories that he was mentioning for me is where, so you have the mixed Hodge structures on cohomology on your object, and then you build a minimal model that will have the mixed Hodge structures on each degree of the model. So it's very connected, I would say. Does this answer?
Yeah, well, sure.
So actually, well, Geoffroy didn't mention another result we have, which is a bit more for non-pure varieties. Then we have this E1 formality functor. And this says, yeah, I mean, the more like classical proof would use minimal models, but then we can use all these symmetric monoidal functors and prove it without models. So.
Cool. Thanks.
There another question?